Okay, I'm going to do a video to explain a few of the problems in the vector math section, which you will then complete the rest of them on your own for classwork / homework. If you don't finish in class, then it's going to be your responsibility to take care of it at home, although we've allowed for you to have plenty of time to finish it in class. And these examples should be more than ample for you to get this done. The formulas are very, very simple. They're on the formula chart for you, so you can use those as you need to. So first of all, I want to start out by pointing out a slight difference in your four-step problem approach, because these are vector math, so a lot of it's going to be visual in terms of drawing vectors. So we have the box that normally says the given information says draw and label diagram. So that's just going to be your vector diagrams as they're needed and as they're appropriate. And you'll use a formula as needed and appropriate. For example, this first one has you determining the total distance. So there's a formula for total distance, and that's just distance total equals your distance 1 plus distance 2 plus so forth and so on if there's more. So this here, the given information is it's got Coach Killian walking 26 meters north, and then he walks 12 meters south. So in terms of drawing these in terms of a vector, so you would do 26 meters north. That vector would come straight up because that's the direction of north. Label that as 26 meters. And then he turns around and goes back 12 meters south. And you could label that one 12 meters, and the direction is pointing south. So you've got those two labeled. So in terms of this, though, you're just going to add them. Direction is not important with distance because that's not a vector quantity. That's a scalar quantity. So total distance here is just going to be 26 plus 12, or the total distance of 38. So now in terms of the vector, the next one says what is the resultant displacement? Displacement is a vector, so now we have to keep in mind the direction. So for displacement, you've got 26 meters, and that's going up, and minus the 12 meters going down. So that's going to give you a displacement for Coach Killian's little marcher on the sideline of 26 minus 12, which is 14 meters. So very different numbers here in terms of displacement versus distance. So that's how you do question number one. Question number two, this is where it starts to get interesting. So now this scenario is that rows a boat is paddling upstream at 1.25 meters per second relative to the water in the river. So that means that her speed, based on the speed of the water, is 1.2 meters per second faster than the water speed. So we'll draw that as a vector, and we'll say so she's going upstream. So we'll just use upstream, and we'll use this as a vector going up, and 1.25 meters per second. That's our velocity going upstream. And now it says that the water flows 0.5 meters per second relative to the bank of the river. So it's going to flow in a direction. So she's going upstream, which would be against the current flow, right? Because water flows downstream. So the water is flowing 0.5 meters per second, because water always flows downstream, because that's what it means to be down. If you're on top of a river, right? If you're on top of a mountain and you're in a river and you're on top of the mountain, so you are up the stream, and then the river by gravity naturally is just going to flow downstream. So you're swimming with this rows of boat scenario. She's swimming against the current flow, so to speak. So now we want to know what is her resultant velocity of her boat relative to the bank. So relative to the bank, so to the water she's going this, but to the bank, because the water is pushing against hers is going to be this minus this. So essentially her resultant vector, and you have a formula on your formula chart, just point that out to you, that says when adding vectors in the same direction, you'll just add the vectors plus, 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 plus. When adding vectors in opposite directions, which is the case here, you're going to add the vectors, but you need to keep in mind the sign. So basically, this one is the positive one, and then this one is going to be the negative one. So in terms of these two particular vectors, right, we're going to do the 1.25 plus a negative 0.5 meters per second. These are both meters per second. And so we end up with a resultant vector, in this case, of 0.75 meters per second. So that ends up being Roosevelt velocity relative to the bank, 0.5 meters per second. And then part B here, so this is part A. Part B asks you, well, supposing she turns her butt around and she starts swimming downstream. So she starts swimming with the flow of the water. So if she turns herself around and she starts swimming downstream, then essentially, right, she's going to turn her vector around. She's swimming downstream. So now these two vectors are moving in the same direction. So now we just add them together and we get a very different scenario in terms of her resultant, right? So the B resultant is going to be 1.75. So quite a bit of difference there between those two. And that's how we do question number 2. All right, so question number 3, this is my favorite question because it has to do with the military. And of course, you know, I served in the military, and we're in pretty close proximity to Veterans Day, so it's kind of a cool question. It says that if an aircraft that is on the deck of an aircraft carrier, those planes are required to reach a airspeed. It's required to have, the plane would be required to go 170 miles an hour to create enough airspeed so that the air would lift the plane up off of the deck and keep it off the ground, keep it flying. And they said that to get this amount of speed in the short launch decks of aircraft carriers, they have to combine a catapult. So they put a catapult underneath a wire, basically attached underneath, and is attached to these rails that'll run along the deck of the ship. And then there's the aircraft, and I can't really draw a very good aircraft here. So you're just going to have to love my aircraft whether you hate it or not. So there's my aircraft, and it's hooked to the aircraft, and it shoots it along the deck. And then, of course, they turn the afterburners on, and it creates some of the propulsion too. But even that is not often enough to launch that, to get the speed that it needs to get that thing off the deck. So the captain of the boat will also aid in this process by getting the boat to move with a vector of 40 miles an hour. And he will turn the boat into the wind so that you have a headwind, so that is creating some more lift of 20 miles an hour. So essentially what happens is you get the vector of the boat going 40 miles an hour, and then you get the vector of the headwind going 20 miles an hour. And this has to be enough to offset the airplane's required 170 miles an hour speed. Oh, and I did meters per second, but these are all miles per hour. So essentially we're going to have vectors going in opposite directions here. So in order to get the required speed for the aircraft, because this is how much airspeed it needs, this is how much it already has before the catapult kicks in, before the afterburners kick in. And so to get the required speed for it, you're just going to use the formula for vectors in opposite directions, which is just the vector 1, vector 2 plus vector 2, keeping in mind the directions. So, and this of course will have 3 vectors. So vector 1, vector 2, and this is going to be plus, this is going to be a minus, this is going to be plus, this is going to be another minus. And so that's what we're going to do. So we'll just say our resultant vector in this case is going to equal 170 miles per hour plus a negative 40 miles per hour, which is the speed of the boat, plus a negative 20 miles an hour, which is the speed of the wind, and that gives us an answer. So the amount of speed that the aircraft actually has to get to is only 110 miles an hour. A much easier possibility than the 170 miles an hour that it would have to get in without the assistance of the boat or the wind speed. So that's number 3. Okay, number 4, you got Claire here is shopping, and she walks 16 meters to the end of an aisle, and then she makes a right-hand turn and walks 21 meters down to the end of the aisle, and determine the magnitude of the resultant vector. So she walks 16 meters to the end of the aisle, so that's going to be a vector drawn this direction, 16 meters, and then she turns right and goes 21 meters. And it wants to know what the resultant vector is. So obviously if we've got these things connected head to tail, we can determine the resultant vector like so. And if we had to measure that with a protractor or use our inverse tangent to calculate the magnitude of the direction if we needed it, but luckily this question here only asks us for the magnitude, so in terms of a formula we only need the resultant vector squared equals the x squared y squared, and then when we do the math it ends up being the square root of the x plus the square root of the y, and here's the hypotenuse, here's your x, there's your y, so these are the components basically of this hypotenuse, and so your x and y are going to be your 16 and 21. So to solve that, it's just going to be 16 squared plus 21 squared, and that's going to give you the magnitude of the resultant vector here. And let me see here what my calculator gives me. Square root of 16 squared plus 21 squared, I get 26.4. So the magnitude of my resultant vector is 26.4 meters. Magnitude only, no direction on this particular question. Alright, number 5. Gymnasium. Walks from lunch to his PE class. He exits the lunchroom and walks 43 meters west. So he's going to go 43 meters west. I'm going to put it over here. So 43 meters west. And then he turns and walks 73 meters north. And determine the magnitude and the direction. So now they want the magnitude and the direction, and this would be the resultant vector here. This is connected head to tail, so you know that the direction here is going to be in quadrant 2. So it's going to be between 90 and 180 degrees. Keep that in mind when we do the inverse tangent. So let's talk about, here's the x component and here's the y component. So in terms of your resultant vectors, you're going to have the x, in this case, is going to be 43 meters, and the y is going to be 73 meters. Alright, and our formulas are going to be to solve for the magnitude. Got the square root, x squared plus y squared. And to solve for the theta or the angle, we're going to do tan inverse of the y over the x. So, a little eraser room here. We'll start out with r equals 73 squared plus 43 squared, and plug those into our calculator. 73 squared plus 43 squared gives me a magnitude of 84.7 meters, and then the direction, tan inverse and the y is 73 over 43. So again, back to my calculator, inverse tan, 73 over 43, and I get 56 or 59 59 degrees. And that 59 degrees is this right here, right? Because I actually didn't keep these straight, so I need to go ahead and make sure that I remember that this 43 here is negative. So if I put that in, I get a number that I can work with, negative 43. And it gives me negative 59. And if I add 180 to that, I get this angle, which is the angle I actually want. Right, so, and that one is 120.5 dead on, so you can go 121 or 120, either one on that one. And so I'm at 121, rounded up. So there we go. That's how you do question number 5 in terms of magnitude and direction. These are exactly the same as the practice work you did in class, just in a word problem format. And then here's this last one here where it basically gives you blah blah blah. I skipped a few. Obviously you're going to need to go to question 8 here. So don't forget we're on question 8. And this says that you've got all of these little things here, and it gives you a scale here of 1 centimeter. So your scale for this question is going to be 1 centimeter equals 340 kilometers. And then it says a protractor and a ruler can be used to determine the magnitude of direction for the following trip. All directions are expressed using counterclockwise from east convention. So that's just what we're used to using, which is 0 degrees here and then all the way around to 360. For each trip, use sine, cosine, and tangent function to determine the horizontal and the vertical components of the displacement. Be sure to indicate east, west, north, or the direction of each component in terms of the 80, or in terms of 0, 90, 180, or 270 degrees. So yeah, so the trip here that they want to follow is, okay, now that I actually have some trips on here. Yours already had these on. So these are the trips that they want you to follow. And so we're going to start out with the trip from Chicago to Denver. So we would take our rulers. So you're going to need rulers for this one. And let me see if I can find a ruler here. A ruler. There we go. Mine's not most awesome because it's difficult to work with. And it's not to scale. So you would take your ruler and you would just place it from Chicago, which is right up here, Chi-Town, to Denver, Colorado. You'd line it up, you'd get your measurements, whatever they are, and that would give you your distance using this scale. So if you got 5 centimeters, you'd take 5 times the 360, and that would give you your distance. But you won't need your distance because you're going to need displacement and the horizontal and the vertical components of that. So you're going to measure the vector, you'll measure the magnitude and the direction using your protractor and your ruler, and then you will calculate the well, actually you're going to measure. This is your magnitude, and I'm just going to make these numbers up because I don't have them handy. So let's say this was 10 centimeters. Let's say the direction of this one, it looks just below the horizontal, so I'm going to say 185 degrees, and I'm going to say 10 centimeters. Again, I don't have a ruler that's going to be to scale, so it doesn't really help, but I'm making these numbers up. You use the numbers that are actually on there. I'll have this set for you, and so then this becomes your resultant vector, right? So this basically is like saying that you've got a resultant vector that is 10 centimeters times this, and you can get back to scale later, but 10 centimeters times this, and it's at 185 degrees. You know how to get the horizontal. The horizontal component is which component, X or Y? So that is the Y component. And then this is the X component, right? And so the Y component is going to be magnitude. So it's R sine the theta. So it's 10 sine 185. And then the X component is R cosine theta. So this would be 10 cosine 185. And you'd plug those numbers in there. And then it just says to tell me if they're northeast, south, or west. And you can determine that looking at the angle. This one is slightly down below 185 degrees, so it's moving. It's going to be going out west, and then this is going to be slightly south. Just look at your directions in terms of that. And then you're going to do from Reno, which is the one out here close to Nevada. So your first one was from Chi-Town to Denver. It was like this one. Right, the second one was, I'm going to erase that one. Second one was from Reno to Miami, so that one is way down yonder. Get rid of this a little bit. So from Reno to Miami. My line's not straight. Your line should be straight. Draw the straight line and measure it and all that good stuff. And then again, you're going to have X and Y. Then the third one is from Seattle, Washington, from Seattle to Washington. So again, all the way back across the country here. See if I can draw a little bit straighter line, something like that. You'll measure that one. And then the last one is going to be from Houston, right here in good old Texas, to Salt Lake City. And Salt Lake City is right there, so that's going to be like that. So those are your lines. Again, use your protractor and ruler, measure your magnitude and direction, then solve using sine cosine to solve for your vertical and horizontal components. So you'll have a total of 4 problems for this one. And hint, 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 this is a very important question. Very star, 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 star important question. Yes, that means you'll probably see it again, maybe like on the test. So get your math done. And if you have questions, text me on Remind 101. Watch my YouTube video, which will basically be this video. You can see it again. And hopefully you'll be ready to go. When I get back, you will be a review for the test, and then we will test Thursday and Friday. So we will test Thursday and Friday. All right, I'll see you when I get back.